Let's work an example using the integral form of the conservation of mass. So just to refresh, here's the equation. This is the conservation of mass, also known as the continuity equation. The first term here is the rate of change of mass in the system, and the second term is the integral over the area. So these are all the different mass flow rates that are going into and out of the system. And all this is saying is that the rate of change of mass in the system has to be equal to all of the flows in and out of the system. Well, I know I put them on the same side of the equation, so in order for this to be 0, this term has to equal that term, equal and opposite. So let's work an example, just a very simple one. Here's a pipe, and this pipe has an inlet at station 1 and an outlet at station 2. Mass is flowing in station 1 and mass is flowing out at station 2. In other words, we can write a velocity here as v1 and a velocity here as v2. We're given that it is steady and that it is incompressible, and we're given that the flow going into and out of these two stations is uniform. So what's that mean? Well, let's start by working with the equation here. So we've got d by dt, integral over the volume of rho dv plus integral over the area of rho v dot n dA, and all that has to be equal to 0. Now, I like to start with the full form and then simplify it any way I can. So the first two things I can do are apply the steady and the incompressible assumption. So steady, well, steady means that anything with a time derivative goes away. In other words, this d by dt is 0 because it's steady. Okay, that's convenient. Just got rid of half the equation. We also have that it's incompressible. Now that this is 0, we can divide the entire equation by rho, because this would pull out, and so this is incompressible. That lets us do that. And so what we're left with, just by applying those two assumptions, is that all we have to handle now is the integral of the area of v dot n dA, and that better equal 0. So now these integrals can be thought of as sums, and you can always split it up, and so we can do an integral over area 1 and a different integral over area 2. In fact, we would want to do an integral anywhere that mass is crossing the border. So we don't need to do anything on the top or bottom surface because no mass is crossing through these solid walls, but these two inlets would both get their own. So now what I want to do is let's work this from the inside out. So we're always going to draw our unit vector, our normal vector for any surface pointing out. So here's n1 and here's n2, and they're pointing out. And so what we want to do is work out what v dot n at area 1 is equal to. In other words, we want to find the velocity vector at 1, and we want to dot it with the normal vector at station 1. Okay, well, v1 can be thought of as a magnitude in a direction. Its magnitude, since it's in the horizontal direction, we use a u for the magnitude in the x direction of the velocity. And so there's the magnitude. Now we need the direction. Well, which way is it flowing? Straight horizontal in the x direction. The unit vector for x is an I hat. Okay, how about the normal vector n1? Well, n1 is pointing straight to the left in the negative x direction. In other words, n1 is equal to minus I. And so we can say that v1 dotted with n1, v1 dotted with n1 is equal to u1 times I hat, that's v1 dot product with minus I hat. Now I dot I gives us a 1, but there's a negative sign here, and so this is just equal to minus u1. All right, well, that's not so bad. Let's try the other one. V dot n at station 2 is going to be equal to V2 dotted with N2. All right, so let's look for V2 here. V2 is a magnitude in a direction. Again, it's horizontal and uniform, and so we can call it U2 for the magnitude. And its direction is also in the positive x direction. Positive x direction, and so it gets a direction of I hat. N2 points out of surface 2, which is horizontal, but now it's pointing to the right, which is the positive x direction. And so this is I hat. And so we sub those together to get V2 dotted with N2, and they are equal to U2 I hat dotted with I hat. Well, I dot I is 1, and there's nothing else going on here. And so this is just U2. All right, so now we got these dot products handled. We can sub those right into our integral. And so this becomes, squeeze it on here, integral over A1 of, let's sub this in, minus U1, that's V dot N1, dA. Actually, you know what? I'd like to show one more step, so I'm going to erase this. What am I doing here? Well, I'm just using this equation. Okay, this is the leftovers from the thing. We want to split this into area 1 of V dot N1 dA plus the integral over A2 of V dot N2 dA. Now, this is V dot N1, this is V dot N2, and so we are just going to take them and sub them in. So let me give you a new page here so you can see what I'm up to. All we need to do is the integral over A1 minus U1 dA plus integral over A2 of U2 dA, and that's still equal to 0. That's just subbing those in from the last step. And now the last thing that we have is that they're uniform, which means we can pull the u's out, and so we get minus U1 integral over A1 dA plus U2 integral over A2 dA. Now, you could sub in differential areas for this, but there's nothing in there, so what's the integral over the area of the differential area? Well, just the area. So we get minus U1 A1 plus U2 A2 equals 0. Or you could write that U1 A1 is equal to U2 A2. Probably something that you saw coming because this was a fairly simple example. The beauty of this is that at any point things could have gotten more complicated and we know how to handle it now. If U1 were a function, say it was some parabola because of the velocity, you could sub in a dA that looks like, you know, dx's, dy's, and dz's, and actually integrate these functions to get more complicated versions of this. And so, just to recap real quick, the process that we followed was we started with the most general form of the equation. We made every simplification that we could thanks to assumptions. Then we worked from the inside out to figure out what all of our v dot n's are. Remember that normal vectors always point out, and so we just assigned the proper directions to them. Then we split this into an integral over each inlet and outlet that showed up in the problem, made the substitutions, and performed the actual integration, which was simple here but could have been more complex in the future.